Hello everyone, and welcome. Today, we're diving into a fascinating and sometimes tricky concept in organic chemistry called rearrangement. Have you ever looked at a reaction mechanism and the final product seems to have its atoms in a completely different place than you expected? That's likely a rearrangement at play. Simply put, a molecular rearrangement is a reaction where the carbon skeleton of a molecule is rearranged to create a structural isomer of the original molecule. It's like the atoms inside the molecule are playing a game of musical chairs, moving around to find a more comfortable and stable arrangement. The main driving force behind this atomic shuffle is the universal quest for stability. Molecules, just like everything else in nature, prefer to be in a low-energy, stable state. In many organic reactions, we form temporary, highly reactive intermediates called carbocations. A carbocation is simply a carbon atom that has a positive charge and is missing some electrons. However, not all carbocations are created equal. Their stability is crucial. A primary carbocation, which is a positive carbon attached to only one other carbon, is very unstable. A secondary carbocation, attached to two other carbons, is more stable. And a tertiary carbocation, connected to three other carbons, is the most stable of them all. This hierarchy of stability is the key to understanding rearrangements. When a reaction forms a less stable carbocation, like a secondary one, and a more stable tertiary position is right next door, the molecule will often seize the opportunity to rearrange. This happens through a process called a 1-2 shift. This means a group from a carbon adjacent to the positive center will literally hop over. This can be a hydrogen atom, which we call a 1-2 hydride shift, or an alkyl group like a methyl group, called a 1-2 alkyl shift. When the group moves, it takes its bonding electrons with it, effectively moving the positive charge to the carbon it just left, creating a more stable carbocation in the process. This shift allows the molecule to reach a lower energy state before the final product is formed. This concept is vital for predicting the correct products in many reactions, especially SN1 and E1 reactions, and is the basis for famous named reactions like the Wagner-Meerwein and Pinacol rearrangements. I hope this explanation has helped you understand the what, why, and how of molecular rearrangements. Thank you so much for watching. If you found this video helpful and it cleared up some confusion, please show your support by liking the video, subscribing to the channel, and ringing that notification bell. Your support allows us to continue making educational science content for everyone. See you in the next video.